Deploying a 70 billion parameter model traditionally requires 280 gigabytes of memory. Standard consumer hardware provides a fraction of that capacity. To bridge this infrastructure gap and execute large language models locally on edge devices, we utilize a critical optimization technique called model quantization. To understand how we shrink these giant models, we first need to look at what a model actually is. It is not code, it is a massive web of connection wherein every single connection stores a unique decimal number called weight. These weights dictate how information flows through the network. When you download an AI model, you are downloading a giant grid of these numbers. For a 70 billion model, that's 70 billion individual decimals. By default, computers store these numbers using a format called FP32, or 32-bit floating point. Think of it like scientific notation, but in binary. Under the hood, IEEE standards allocate 1 bit for the sign, 8 bits for the exponent power, and 23 bits for precision. That's 32 bits of physical hardware space for every single number. Now let's do the math. 32 bits times 70 billion parameters divided by 8 equals 280 gigabytes. That's a huge amount of space. But if we drop down to 16-bit half precision or 8-bit integers, the memory size drops down. Quantization is the art of converting these massive 32-bit decimals into lightweight integers, like int 8, int 4, or even lower. Here's the secret that makes this possible. If you plot the weights of a trained large language models on a histogram, they don't use the entire range of FP32. They cluster tightly in a narrow band. That means a large portion of the digital space on precision is left unused. So to map these continuous decimals into discrete integers, we use two primary strategies. That is symmetric and asymmetric quantization. In symmetric quantization, we take our floating point range from -3 to +3 and map it evenly across the discrete slots of an 8-bit integer. We use a single constant scale factor to compress that range. A 0 in floating point maps perfectly to 0 in the integer space. The mapping is mirrored and fast for the hardware to calculate. Just like that, your weights take up 1/4 of the space. But symmetric quantization has a major limitation. It assumes your data is perfectly balanced around 0. So what happens if the model weights are heavily skewed, ranging from -1 to +3? If we use symmetric mapping, we are forced to mirror the scale out to -3, leaving the massive empty gap on the negative side. This means we waste half of the 256 integer slots on empty space. To solve this, we use asymmetric quantization. Instead of forcing 0 to stay in the center, we shift the origin. We map the true minimum value to -128. And the true maximum to 127. To do this, we introduce an integer offset called a 0 point. This extra variable ensures that real-world floating point 0 is still perfectly represented, allowing us to utilize every single bit of the integer 8 spectrum with the maximum efficiency. So, quantization maps these massive models into a lightweight integer-based version and maintaining the same exact architecture with the minimal accuracy and loss, making it small enough to run perfectly on edge devices like phones, laptops, and IoT chips like, for example, the ESP32. And that's quantization.